Myself, Dr. W. Gandure from Kamlanini Mahavidyalaya, Nagpur. Today I am going to discuss the Latimer diagram, Frost diagram and the Pourbaix diagram. Latimer diagram are used to identify the redox potential of species in a different oxidation state. And both Latimer and Frost diagrams are used for to identify the redox, and both are the redox diagrams at particular pH, and also we are going to see the Pourbaix diagram which are at particular pH. So all these three diagrams of various species we are going to see here in today's presentation. Latimer diagram of chlorine and oxygen, and Frost diagram for that is for the oxygen, and Pourbaix diagram for iron. These diagrams we are going to discuss in today's presentation. So today's topic is Latimer diagram, Frost diagram and the Pourbaix diagram. So we are going to discuss all these redox diagram of particular species. And first is a content, and topics are here. Latimer diagram of chlorine, Latimer diagram of oxygen, Frost diagram for Latimer diagram, Frost diagram of nitrogen, Pourbaix diagram and Pourbaix diagram of iron. All these are the part we are going to discuss. And first is a Latimer diagram. So in case of Latimer diagram, what do you mean by the Latimer diagram? How it is a redox diagram. So as a Latimer diagram for an element present potential data for series of compound of element in which it is present in a different oxidation state. The most oxidized form of the element is placed on the left, and the species successively on lower oxidation state are placed in the decreasing order of oxidation state. And these are decreasing order of oxidation state diagrammatically shown A to B and B to C, and there are a number of applications of this Latimer diagram. And first point is shown here in the slide: speciation of element. So Latimer diagram gives a clear idea about all the possible species of any element that can exist in a single class. Another point is that stability of the species. The redox stability of the species depends upon its reduction and oxidation potential. The values of redox potential give an idea about the thermodynamic stability of the species. So one species undergo different oxidation state, and in one glance they are showing which species is stable or not. Third point is that redox potential of non-adjacent species. It is also possible to calculate redox potential of non-adjacent species using the relation between free energy. And for this case we are going to take the one example, and that example, consider the Latimer diagram of for example, Latimer diagram shown here in this way: A to B, B to C, and these are the redox potential and or reduction potential. Let the number of electron accepted are n and n dash. Number of electron accepted are n dash, n2 dash in the two step, and free energy change in the two steps are also corresponding respectively. We can represent it delta G0 dash, delta G0 2 dash. And the redox potential of the couple A/C, these two species can be calculated as given here. So total free energy change equation we can write delta G0 total energy change equal to delta G0 dash plus delta G0 2 dash. We know the Nernst equation, that is free energy related with the electrode potential. Delta G0 equals to minus N F E 0 and minus N0 equal to, also we can write this one because delta G0 equal to this one, and so we can write for the one delta G for this case. So this equation plus this equation. So Ne0 this common F can be cancelled, and we obtain this equation. But total number of electron inward are N equals to N dash upon plus N2 dash. Therefore we can write E0 equals to N comes here, so total number of electron N equal to this, so we have this divided by N dash plus N2 dash. For example, reduction potential of this couple is given by, this is the equation. This equation we have to use to find the redox potential or reduction potential of that species. And if we know the values of this N dash, E0 dash, all these terms, then it is possible to calculate the value 1.19 volt. So in this way, in case of by using the Latimer diagram, reduction potential of any couple is the species can be calculated. So another now here, so example we are going to see the Latimer diagram of the chlorine. And before going to see that also, here fourth point is also there, that it is possible to predict the disproportionation of the same species in the aqueous medium using the Latimer diagram, and this explains why that with the Latimer diagram of oxygen. So this disproportion we also explain with the help of Latimer diagram of the chlorine. So here now we are going to discuss the Latimer diagram of the chlorine. So in this case, Latimer diagram for chlorine in acidic solution is given here, and this is for basic solution. In the acid solution here, so see the different species undergo the oxidation, and here +7 oxidation state, +5 oxidation state decrease means undergo. And here on the arrow shown the reduction potential. So in this way, this is the oxidation state in a decreasing order of the Cl. Here Cl is 0 because this is the molecule, and here -1. Here it is, if you calculate oxidation state, we can calculate here +1. So in basic condition, pH 14, Latimer diagram of the chlorine is given by, these are the and this is the reduction potential. So this is the first diagram for in a acidic medium, second is in a basic medium. An important feature of this diagram of Latimer are given here. From this diagram we can say that the important features, and these features are, first point is that the number below each species give the oxidation state of that element. So the +7, +5 are the number which is the oxidation state of that species, chlorine. And second point is that the species with highest oxidation state is placed on the left. The oxidation state is +7 in case of acidic, +7 in case of basic also. So this is the higher oxidation state, and successive lower oxidation state are present to the right hand side. So it decreases in this way. The reduction potential of each couple is shown on the arrow. So the reduction potential is shown on the arrow. The value shown on the arrow is the reduction potential. Number 4 is reduction potential of Cl2/Cl- is same in acidic and basic medium. This is because reduction of chlorine does not involve H+, and so the pH does not affect this reaction. Other couples are affected by the pH. So in this way, these are the important feature of this Latimer diagram of chlorine. Another example is there, Latimer diagram of oxygen. So in this case, the Latimer diagram of oxygen can be shown as shown here. And this diagram is shown, and here oxygen has zero oxidation state because it is an element, and in this case it is having -1 oxygen. Here oxygen have -2 because H+ have +1, 2 are there +2, so oxygen have -2. We can calculate it. And this Latimer diagram for oxygen also have some important features, and there are 3 species of oxygen in the 3 oxidation state. 3 different oxidation state are there of oxygen. And second part is that reduction potential are shown on the arrow of each here. Again here these are the reduction potential values are given for that couple, and diagram can be used to predict the disproportionation of hydrogen peroxide as given below. So here this water undergo dissociation forming H2O, and here H2O2, this is hydrogen peroxide and forming oxygen. And it can also feasibility of this reaction by using Latimer diagram of oxygen in acidic medium can be shown in this way. So O2 and forming this same reaction, and here oxidation states are different, and 2 half cell reaction can be written as one is H2O plus H plus, and taking 1 electron and forming 2 H2O, oxygen plus 2 H plus, and forming adding 2 electron and forming H2O2, and their corresponding reduction potential, and substituting the 2 equation we get common terms can be cancelled, and 2 H2O equals to H2O plus O2, we get this equation. Since the value is positive, here for this after subtracting the equation each value is positive, and this positive value indicates that disproportionation of hydrogen peroxide is a spontaneous. If it is negative, it is not spontaneous, but it is positive, so it is a disproportionation. Disproportionation means the same species undergo in different oxidation state and undergo the process, and this is known as the disproportionation, and here the disproportion of this H2O2 is a spontaneous. So these 2 are the examples. Another diagram is there that is given by the first, and Latimer diagrams are useful in identifying the reduction potential of the different species However, the complexes in many cases also, but in manganese there are 5 reduction potential in acidic condition and 5 in a basic condition. Hence it is become difficult to draw detailed quantitative information. Therefore, to simplify the diagram and make it qualitative so as to get necessary information at a glance, we have to consider here the first diagram. And for this case, for the first diagram, consider the element X, which exists in the number of oxidation state in the, and after considering the redox couple of this Xn plus upon X0 due to the gain of En electron, standard free energy is related to the standard reduction potential H. So standard reduction potential can be shown in this way: delta G0 equal to minus En F E0 and minus delta G0 upon F equal to En E0. We have to plot a graph here. Graph is plotted between minus delta G0 upon F or En E0 here shown, and we assess the oxidation number and we obtain such type of graph, and this graph is known as a first diagram. This diagram is known as first diagram. When a graph is plotted between En E0 in volt and oxidation number, the curve obtained which is known as the first diagram of that species. And now important feature of these diagrams are about this diagram. So here this diagram, according to this diagram, first point is stability. Most stable oxidation state is the one which has minimum value of Ne0. Hence species B is the most stable in this diagram. So which is having lower value Ne0. So B is having A, B, C, D, E are the points. So B is having this A and C are joined by dotted line, but now B is having lower value of Ne0, therefore it is a stable and most stable species. And second point is that comproportionation. If we join two adjacent points and the middle one lies below the line joining the two as shown in the dotted line AC, and below this there is a B point. Two extreme species A and C have tendency to undergo comproportionation to give the species B. So here if you join the 2 points A and C, the 2 points are joined by shown by the dotted line. A and C are joined, and below this there is a B. So this B is a point where these are separated, and in this case these are the 2 extreme cases of A and C and tendency to undergo comproportionation to give the species B. So this is one part. Another similarly part is the disproportionation. If we join the two non-adjacent points, the middle one lies above the line joining the two as shown in a dotted line CE. Similarly, disproportion is there, CE here, CE. So C is the dotted line and D is the disproportionation point. And in this case, D has tendency to undergo, the point D has tendency to undergo the disproportionation to give the point C and E. In this way, and another point is that reduction potential. Higher is the slope of the line joining any 2 points, higher is the reduction potential. If you join the 2 points and if you find the after joining this or this joining, and if you calculate the slope of that line, if it is higher, then it is having higher reduction potential. For example, in case of slope of the line CD is more than the curve BC, and therefore reduction potential of couple D by C is greater than C by B. And redox stability, another point is there. Species B is the prone to oxidation and species D is prone to reduction. So it favors the oxidation and reduction. So all these points have been shown here. Important features of that first diagram: stability, comproportionation, disproportionation, reduction potential, and redox stability. So redox stability of B is prone to oxidation and species D is prone to reduction. So these are the important features of this first diagram. And this is the first diagram from Latimer diagram. So here it is shown that oxygen exists in the 3 oxidation states: 0, -1, -2. They are shown by Latimer diagram in acidic medium, and it is shown here this proportionation 3 oxidation state of oxygen here: 0, -1, -2, and a standard state of oxygen is O2. and the molecular oxygen of volt equivalent is given by Ne 0 equal to 0 volt. The volt equivalent of hydrogen peroxide is given by Ne 0 equals to, if you calculate this value, answer is coming minus 0.70 volt. It means that volt equivalent of hydrogen peroxide is 0.70 volt, more negative than oxygen. The redox potential of water is given by E 0 equal to, this is the equation we have seen already. After putting all this value, the value is coming 1.23 volt. Volt equivalent of water is given by, in this way we can calculate the volt equivalent of water Ne 0 equals to minus 2 1.23 into, so equals to minus 2.46. This is the value. It means that the volt equivalent of water is 2.46 volt, more negative than oxygen. Since the standard state of oxygen, this potential 1.76 volt more negative than H2O2. Therefore, first diagram is can be shown for this here. In this way we can show, and also in this way, if you join H2 and O2, then we show in this way the diagram. So these are the diagrams obtained from the Latimer, and these are the first diagram for the species water. And here in this case, important feature of these are the slope of the couple H2O2 or by H2O is higher than that of O2 oblique H2O2. It means that reduction potential of H2O2 oblique H2O is more than that of oxygen by H2O2. Water occupies the lowest position in the plot, and so it is a thermodynamically more stable. Water is below here shown, so water is here at the bottom, so it is more stable, and these are the unstable species. And after that, we if we join the 2 points corresponding to the H2 and O2, we get the diagram as shown. And it should be noted that the point H2O2 is above H2O2 is above the line joining H2 and O2. That is, H2O2 is unstable and has the tendency to undergo disproportionation. So after joining these 2 points, H2O2 is there, and it means that H2O2 undergo disproportionation. And here, so these are the important features of this first diagram. And the first diagram for nitrogen is very important, and first diagram for iron in acidic medium shown by the solid line, and basic medium shown by the dashed line in this figure. So this is the this is solid line here, start from this, and this is the dashed line for this basic medium, and this is the most stable. And in case of a solid line, in case of solid acidic medium, NH4 plus is the most stable, and in case of second, nitrogen is the most stable species in basic medium. So again, from this now, important feature of this diagram can be shown here, that it is shown here. Important feature of this diagram, NH4 plus is the most stable species in acidic medium, while N2 gas is the most stable species in the basic medium, since they have lowest value of Ne0. It is easier to reduce HNO3, N2H4, HNO2 and NO in acidic medium because slope of the redox couple are positive. But it is difficult to reduce the NO3 minus and NO2 minus in basic medium because the slope of NO3 minus upon N2O4 couple and NO2 minus by NO couple are negative. It means that their reduction potential are negative. The 4 species NH2OH, NH3OH plus NO and N2H4 lie over the line joining their neighbors, and so they have tendency to undergo disproportionation. So these are the species which undergo, because after joining they are between that, above that, and therefore they undergo disproportionation. So these are the 2 diagrams, Latimer and first, for the species. Third diagram is also very important, that is a Pourbaix diagram. And so these Latimer diagrams used as well as for and also first diagram. Both the diagrams are redox diagram at definite pH, and above diagrams shown either at pH 0 acidic medium or pH 14 basic medium. However, it is necessary to show see the effect of pH on the redox potential and various equilibria in the solution. This has been done by Pourbaix diagram. In short, we can say that Pourbaix diagram are the plots of redox potential with versus pH, and these diagrams shown in the figure, and it is shown, these are important features, and Pourbaix diagram is shown here for the iron. And important feature of this Pourbaix diagrams are here are the each line represent the boundary between the 2 species. Each area represents the condition of pH and potential E under which particular species will exist in the solution. The area between the dotted line represents the stability field of water. A horizontal line parallel to x-axis represents the purely redox reaction independent of the pH, while vertical line parallel to the y-axis represent non-redox reaction that depends upon the pH. And another is that a slanting line represents redox reaction which is a pH dependent. The line having a negative slope represents reduction reaction in which H plus ions are on the left hand side of the equilibrium. The line having positive slope represents reduction reaction in which H plus ions are on the right side of the equilibrium. So these are important features and points of this Pourbaix diagram. So this is the Pourbaix diagram for iron. This is the vertical line AB, BD, and then DEF. DE is the vertical line, BC is the vertical line. So the lines which are horizontal are showing redox reaction, and those are vertical are non-redox. And different points are there. So one by one we are going to discuss the points of this diagram. First is a line AB. So here line AB is the redox boundary between the Fe2 plus and Fe3 plus. So it is in a figure shown Fe3 plus and Fe2 plus. So this is the equilibrium between the AB line here, Fe3 plus Fe2 plus. So this is the couple, and Fe first point Fe3 plus gain 1 electron and convert into Fe2 plus. This is the reduction. So line AB is the redox boundary of couple Fe3 plus by Fe2 plus. This equilibrium can exist only at lower pH. The reaction shown as we have seen. As the reaction does not involve term H plus, the redox potential is independent of pH. Hence, line AB is a parallel to pH axis and represent purely redox reaction independent of pH. If the solution contains any species having redox potential above line AB, will oxidize Fe2 plus to Fe3 plus and to Fe3 plus will predominate in such solution. So this is line 1, and another line is a line BC, and line BC is a vertical line. This is the vertical line, and this shows the vertical line indicate shown here. This line corresponds to the hydrolysis of Fe3 plus as shown. Hydrolysis of Fe3 plus is taking place in this way. So line BC, Fe3 plus undergo hydrolysis forming ferric hydroxide and 3H plus ion. In this way, this Fe3 plus undergo hydrolysis, and shown in this figure, vertical line Fe3 plus is there, and this reaction is not a redox reaction because oxidation state of Fe does not change in this reaction. It only undergoes hydrolysis. Since the reaction involves H plus ion, it depends upon pH. Lower pH favors Fe3 plus ion, while highest pH favors formation of ferric hydroxide precipitate. Since the line is vertical and parallel to y-axis, it represents non-redox reaction. As we have seen that vertical line is a non-redox reaction. Horizontal are the redox, but vertical lines are non-redox reaction, and Fe3 plus undergo the hydrolysis and forming this type. We have seen the hydrolysis reaction. So it favor depend upon that. This is the second point, and so important feature is there. So lower pH favor the Fe3 plus ion, while the higher pH favor formation of ferric hydroxide. So at higher pH, so lower pH is Fe3 plus, but when as pH increases here, then it undergoes the hydrolysis and become ferric hydroxide. So we know that at higher pH Fe undergo hydrolysis, and so at lower pH it is Fe3 plus, but when the pH is more, then it undergoes the hydrolysis. So this is the second line BC, and now third line is a line BD shown. So line BD shown here. This is the slanty line BD, and in this case along this line two species Fe2 plus and FeOH thrice are there along this line BD line, Fe2 plus and FeOH thrice. These are the two species are in equilibrium. This is a redox reaction because this is slanting at higher pH. When Fe3 plus exists as its hydroxide, the reaction can be shown. This reaction of line BD, if ferric hydroxide plus 3H plus and accept 1 electron become Fe2 plus. So in this way the equilibrium can exist between these two species. And here in this diagram we can say that from this diagram that for that reaction, the reduction potential is also given by the Nernst equation, and here that reduction potential is shown. This is the reduction potential can be obtained. Reduction potential is given by the Nernst equation. This is the Nernst equation, and by putting this is equals to pH, so we can write E equal to V0 minus this value is coming 0.5059 because natural log to the base 10 Fe2 plus minus 3 into pH. So this equation shows that with the increase in pH, so in this line BD indicate that line BD, two species are in equilibrium, and this equation shows that with increase in pH the potential goes on decreasing as represented by the line BD. Negative slope of the line indicate presence of H plus ion on the left hand side of the reduction equilibrium. So this is line third. Now number 4, line number DE, another DE is there. Again this is line D. This is the line DE which shows this line correspond to the reaction, and reactions are shown here in a reaction is shown here for the fourth Fe2 plus water undergo hydrolysis and forming ferrous hydroxide and 2H plus. So this is the line DE shown in the diagram, and from this diagram we can say that this is not the redox reaction, since the oxidation state of Fe2 plus does not change. Since the reaction involves H plus ion, it is pH dependent. Formation of ferrous hydroxide is favored by highest pH. The vertical line parallel to y-axis represents the non-redox reaction, and the vertical line, this is not vertical, but this is the reaction DE at higher pH, and therefore Fe2 plus converted into FeOH twice. But oxidation state is same, therefore it is not a redox reaction. And one more line is there, and that is a line DEF. After BD, after DE, this is the vertical line. DE is the vertical line, therefore it is a non-redox. So this is the vertical line, it is a non-redox reaction. And one more is there, DEF. This is the DF, and line correspond to the reaction, and in this line FeOH thrice and accept and convert into FeOH twice. So reaction shown here for this line DF, FeOH thrice plus H plus 1 electron and FeOH twice. So this is the redox reaction. Potential is given by the Nernst equation. So this is the equation, E equal to V0 and log equal to this. So in the similar way we can also find the E equal to E0, that equation is there. We can find out the redox potential for this diagram. So this is the diagram, and DEF is the line, and feature of this line is that from this line we can say that with the increase in pH potential goes on decreasing as shown by the line DF. Also the negative slope represents H plus ion on the left side of the reduction equilibrium. So the values shown here of redox potential in the graph, so equal to E equal to E0 minus 0.0591 pH. So we can calculate the redox potential for this also. And so this is the Pourbaix diagram for iron, an important feature of that Pourbaix diagram. So we have seen today the Latimer diagram for chlorine and oxygen, and first diagram for nitrogen, and the Pourbaix diagram for iron.